Log on, tune in, find out. Another good idea from Cambridge.
Please welcome Joyce McLaughlin from RPI. She's going to talk about biomedical imaging in tissue using time-dependent data.
So I've been working on this problem now for about 10 years, and what we are interested in is using biomechanical imaging as a diagnostic tool. So up until this last 10 years or so, this was definitely not done. In the kinds of imaging modalities that you know about, like CT scans and ultrasound and also MR, aren't using these same properties. And to begin with, we were thinking, well, now what we're going to do is we're going to replace everybody because we were very excited and all, but now we are thinking more that we will work in collaboration with people, and there will be a number of images on the screen, and they will use that collectively as a diagnostic tool. Today when I'm talking, I want to talk about work. I'll present work that's joint with Dan Rensselaer and Jens Klein and Quy Lin. They're all former postdocs, and Quy Lin is also a former PhD student of mine, together with Ashley Thomas and then Jean-Marc Yoon, who is at Clemson University now. We have a current working group, and as we were just discussing, we have a couple of mechanical engineers, Antoinette Maniati and Asad Oberai, who are both finite element people and very good modelers. Then again, some of the same people there are repeated down here, and in addition there is a mechanical engineering student, Yishao Zhang, two mathematical students, Jessica Jones and Ashley Thomas, and Ning Zhang, who is now at the University of Pennsylvania Medical School. Again, as we were just discussing, you really need experimentalists. No one is going to pay attention to what you do unless you are looking at data. And I am that close to the applied problem now, so we work with Matthias Fink at ESPCI, who is probably familiar to most of the inverse problems people here in the room, with Kevin Parker, who is a biomedical engineer, and Deb Rubens, who is a radiologist at the University of Rochester Medical School, Richard Ehman, who is a radiologist at Mayo Clinic, and Ingolf Sack, who is a biophysicist in Berlin. Okay, so what are the properties of tissue that really motivate what we're doing? First of all, tissue is 80 to 90% water. But it's not entirely water. I often say that we're not puddles slithering around on the ground, that in fact we have structure. And that structure comes from the solid matrix, and tissue is then elastic. It supports both a compression wave and a shear wave. What's powerful about this, though, for us, from the point of view of mechanical imaging, is that the compression wave speed is about that in water, which is 1540 meters per second. And the shear wave speed, because we are mostly water, is very, very slow. You can almost watch this wave. It's 3 meters per second. Well, on average, of course, different tissue types have different speeds, but it increases quite a lot in abnormal tissue. So a typical thing is to have 100% increase. We might even have 200% increase. Now, what we're building on is the doctor's palpation exam, which is centuries old, and it detects shear stiffness. I'm sure probably everybody in the room at some time or another has had the doctor press against the surface of the skin and push the hand back and forth to detect some kind of abnormality below the surface of the skin. In fact, this particular exam is still the leading diagnostic tool for breast cancer. More breast cancer is first determined by palpation than any other method. Now, the body is unbelievably resilient to vibration. And in our case, the experiment we're going to have, the tissue is going to be under displacement for milliseconds, for a very short time. The amplitude is on the order of tens of microns. We'll use linear models. We will assume, because I have time-dependent data, we'll have some sort of source, like a pulse, for this particular talk, although sometimes we do single frequency excitation. That's a completely different talk. Okay, and we will assume there isn't time really for the fluid to flow through the matrix. So we're not looking at fluid matrix models. We are now looking at those for when we model disease, but that's another completely different talk. Tissue is viscoelastic, and we want to talk about models that are going to give us this viscoelasticity. Whoops. Okay, so the slide that I just skipped is a slide where I want to convince you that the things I told you about shear wave speed are true based on experimental data, but I think I'll skip that talk, that today a few people in the room have already heard that. Okay, so let's talk a little bit about the experiment. So one of the most promising experiments has to do with something we call interior radiation force push. Now, if tissue was just purely elastic, this experiment would not work. But because it's viscoelastic, it does. We have an ultrasound transducer here. It has about 128 element array, and you can focus the beam from the ultrasound transducer on particular points. And when it's focused, it produces a push. And what Matthias Fink and his student Jeremy Burkhoff learned was that they could make a sequence of pushes down a line. And when they did that, they effectively had a line source. Depending upon the speed at which they did that, the speed was faster than the shear wave speed. What propagated away was some sort of conical wave. So they had a wavefront when they did that. Now on this slide, I also have an ultrasound image, and this is an ultrasound image from a woman who they knew by palpation and also by biopsy, about a 1 centimeter cancer here. And in fact, she had this breast removed, and you can see in this particular image that we don't see anything. So this was part of the reason why we were thinking, oh, well, we'll just try to do better, but now we're thinking we'll work in collaboration with people.
No, I don't understand the previous image, I'm sorry. So what were we supposed to see in the previous image?
We were supposed to see
nothing.
Well, we see nothing, but we were supposed to see an inclusion here,
Yeah.
a cancerous inclusion.
But we don't see anything, okay.
We don't see anything. This part that we see here, these are the ribs.
I understand.
Okay, so let's take a look here. What's happening? So what we want to do is the following. We have this ultrasound transducer here. We're going to send in RFIQ, we're going to send in a pressure wave, and we're going to take RFIQ data sets. And in this sort of pictorial slide, what I've indicated is that we have speckle images at different times. In fact, we don't actually compute those speckle images. We simply use the RFIQ data set, the time traces that we get from this. What we want to do then is look, you can think of it in terms of the speckle image, we want to look at each little piece of tissue and try to correlate this little speckle that we see as we go from frame to frame. And when we do that, we see that by that correlation we'll get a movie. And a typical movie would look like the one that I'm going to show you here on the right. When we show this movie, what we have here, before I do it, is there's an inclusion here. This is a phantom in the laboratory, and you're going to see a wave propagating from the right. And as the wave goes through the inclusion, you'll see the front of the wave push forward because it's stiffer in that inclusion. Okay, so let me show you this wave. So you can see the wave moving forward, and then you can see, well, now we see there's a lot of scattering. I'll do it again. So right about this region in here, in the beginning, you're going to see the push forward. There we go, right there. So what we want to do is use that front. And for the purposes of this talk, that's what I'm going to use. We have many different ways that we address this problem. Oops, I didn't mean to do that. Okay, so just to give you an idea of how this is actually done, it's just a glimmer, really. You can think of the following. Suppose that I send in a plane wave from this ultrasound transducer. And then I have this small scattering volume here, and what scatters away is this circular wavefront. And the information here that we see from each one of these pieces is recorded on each element in the array, and I've done this by showing this little time trace. Okay, so of course right below, right above this scattering volume, we get that received signal first, but then at the other ones later. So what's done then is by assuming that the compression wave speed is constant, we then figure out where these little pieces of time traces are relative to the scattering volume and add all of them up. Of course, we have scattering everywhere else too, but the idea is that that's random enough that we'll get cancellation. Well, okay, that's experiments. Okay, now we add all that up, and for this little scattering volume, we have a time trace. Okay, so for each one of these, we have a little time trace, so each one of these little pieces of signal we can associate with a scattering volume. And then what we do, as I forgot to say in the beginning, is because we have this big change in the speed of the pressure wave and the shear wave speed, we assume that the shear wave is essentially fixed when we take an RFIQ data set. So we go from frame to frame, that means we're about 1/3 of a second, and we have these time traces, and so we look for the little piece of time trace that correlates best in the next frame. And this is done with cross correlation. We look for the peak in the cross correlation, and from all of those computations, we create a movie. Okay, so now I'm going to show you another movie to give you an idea of some of the things that can happen. So here I'll show you two things. There'll be a movie at the top and a movie at the bottom, and in each one there'll be an inclusion. It's actually an anisotropic inclusion. This is a phantom in the laboratory. In one of these, we'll start with the pushes near the top and come down. And then we'll see the conical wave will have a shape which is wide at the top and narrow at the bottom. In the bottom one, we'll see that we start at the bottom and go up, and so the conical wave is narrow at the bottom and wide at the top. Let's see, anything more? Okay, so let me just remind you, there's an inclusion here. We'll see the push forward because it's stiffer. Okay, let's do this. Okay, you can already see the push forward here, but you can see the data is fairly noisy when we get this. So now if we calculate the arrival time using a cross correlation effect, which is a standard method, and when we color code what the arrival time is of the front, we get something like this, and you can see it's really extremely noisy. It's a problem for us. Okay, now what I'm showing you so far is a movie of the downward displacement. We're talking about elasticity. We have displacement in the downward direction, in the transverse direction, and into the image plane. Now, what we are beginning to get are displacements that, and the reason we show mostly the downward displacement is because we have this very fine discretization in time associated with this, the downward push. Now, in order to get the transverse displacement, then it would be much more difficult, and we wouldn't have nearly that kind of discretization. And so what's done is, when one does this, is one first gets the downward component and then takes the array and then just slants it. And so then we get a component, say, in this direction, and by combining those we can get, with very fine discretization in time and space, and then we can combine those and get the transverse component. So that's what we're beginning to get from GE, and I'll just show you a couple of these. Okay, so we made a push here. Here's the downward component, and the one over here is the transverse component. I'll do it again. Okay, the one on the right is the transverse component. The one on the left is the downward component. Okay, but entirely in this talk I will talk about wavefronts. Okay, what we would like to do, this is the set of arrival time curves. We have a nice circular inclusion here. We want to use these arrival time curves to recover the position and also the increase in stiffness of this inclusion. What's the model? Okay, we started out thinking elastic. Maybe elastic models would be enough. We've never changed from linear because we had the amplitude of displacement is so small. So this is a typical system of elasticity equations where we have two Lamé parameters. The first Lamé parameter is lambda. That's the one that's so big. And the second one is mu. This is the one that's much smaller. Okay, tissue is mostly water, so it's nearly incompressible. So this helps us in the model if it's truly elastic, and allows us to eliminate this part of the strain. So epsilon, I use that a lot. That's the strain. This is a matrix. It's the gradient of u. U is a 3 vector, and this is its transpose. The strain is a symmetric tensor. Okay, frequently, as I was just explaining, we only get one component. We get the downward component. This is a problem. Okay, we have to find an equation that just the downward component would satisfy, and we do this by throwing this away, which we can argue fairly well can be done because of this. We would like to get rid of this term. This is actually quite hard for us to get rid of. Because lambda is so big, even though this is small, really the product of this is a pressure field, and that's order 1. But we do it because we don't have anything else. Now,
so how do you justify that? Is part of the fact that lambda is large, you say, why do we throw this term?
We throw this term away because we can't compute it.
I see.
I mean, this, yeah, it's not a, I'm being honest here.
No, of course, that's the only way to do it, I understand.
Okay. Okay, we now, for the purposes of this, I'm just, well, okay. And we wind up with this. Now what I'm talking about is wave fronts. So for wave fronts, it's maybe not so critical because the wave front, probably the Eikonel equation that we get from this, it would be very similar to the one we would get from this. A fundamental property that we have for the elasticity equations is that we have finite propagation speed. And of course, we see in the experiments that it looks like we have finite propagation speed. So we definitely want that. Okay, so we need viscoelastic models. We need this because the experiment is only true if we have a viscoelastic model. So we need it for many, many reasons. Okay, so what we're using now is the linear solid model. What are the properties here? The properties are that we have this integral term. So we have this standard term that we would see, this stress-strain relation that we would see in the linear elastic models, but in addition we have this integral term. So we have this integro differential model. This integral term tells us that we have memory. So the wave remembers what happened before. If we are looking now for only one component, again, we throw this term away. Notice that I include this memory term only for the shear moduli and not on this first Lemay parameter. And we do that only we could do it here, but we can match the data pretty well without doing it. So that's a good, reasonable reason. Okay, if we have only one component, again, we throw this away and we get another integro differential equation, but with only one component. Let me describe these things a little bit. We get this by doing the following. The inspiration for this model is that we have a spring, and then we have a series of spring damping spring dashpot models, and all of these, that's called a Maxwell element, and all of these are in parallel. Okay, let's talk a little bit about what this means. When we send a wave through and we have the wave front, what happens is all of these springs become active, but at the wave front, the dashpots are not yet active. Okay, so at the wave front, what we see is all the springs. Now the standard experiment in the laboratory for finding Young's modulus is to take a piece of material and squeeze it. And then when you squeeze it, you compress it. And then you wait, the material relaxes, and from that, seeing how much it compresses, we get Young's modulus. When that happens in this model, all of the dashpots will be fully engaged. We won't see any of these springs. And so when we do that experiment, it's this term that we get. So that's important to know when we're trying to match what happens in the experiment in the laboratory and what we get for the wavefront. All of these terms, these mu alphas, these additional spring constants, you can think of them, or their additional moduli, are positive. So we get a faster speed. What else we see here, and we should see in a viscoelastic model, is that if we look at individual frequency content, then we should see different speeds. They should be frequency dependent. And I've written this down here, although I'm not in the frequency domain for this talk at all. Okay, the tau, the relationship of these is the relaxation time for each one of these. Typically we find them to be of the order 10 to the minus 3. And a recent comparison with experiment by Antoinette Maniati and one of her students, Kristen Lee, who is in our, they're in our group, they show that they could get fairly good qualitative agreement with just 2 of these.
And excuse me, and these constants, you choose them or you determine experimentally?
Well,
the etas and the mu's?
They determine experimentally. We actually mostly look for tau alpha and mu.
As well as the number. So you decide experimentally how many you will take, yes? Capital N, I mean.
Well, we decide mathematically how many we need in order to get a good match.
I see.
And then we determine what they are. Well, simultaneously, we're determining what they are. We only pick 2, we can't get a good match, we take 3. Okay, we need some theory for these models. So we have these models, these integral differential models, and the first thing we want to show is that indeed we do have finite propagation speed. Okay, so this is a result with Jean-Marc Youn, and the way we did this, it's sort of a typical way, but it's not. But there are many other ways. We assume that we have some, you can think in 3D. Of course, I can't draw the picture quite like that in 3D. This is time on the vertical axis. Here I have this disk of radius epsilon, and what we establish is that there is a space-time cone here. If we start out initially at rest, there is a space-time cone here where the solution stays 0. And from that we know that we can't have our wave zinging in at infinite speed from the side here. Okay. Okay, we also have the weak solution formulation and the existence uniqueness of a weak solution and the regularity results. So these regularity results here at this level of the weak solution are very similar to the ones we would have if we didn't have this integral term. However, if we look at higher regularity, which is on the next slide, so I could pause here and you could take a better look at this, but I think the real point here is that we have a weak solution formulation with a bilinear form here, and we are able, once we move it into the right formulation, to use the Lax-Milgram theorem here, and of course we have the time-dependent version here. Okay, and then when we go to show more regularity, then things begin to change slightly. We need more regularity on the initial velocity in order to get the similar kinds of results that we might see for the elastic system. So of course when we get this additional regularity, we must assume additional regularity on the boundary as well as the additional regularity on the initial conditions and the right-hand side, the forcing term. Okay, now we do this because we want to compute simulated data. I mean, you need to also do this in addition to using laboratory data. Okay, now what we're looking at now is a system of 3 equations we want to simulate in 3D. This is not a small problem. Okay, so what people often do is, or what they would like to do, is simply make the domain very, very large and put some known boundary condition out there. But in fact, that really doesn't work from the point of view of size of problem. So let me just describe a little bit. Oh, let me just say this paper here will appear in a contemporary mathematics volume, probably in early January. Okay, so this method was in JASA in 2010. So what we want to do here is somehow compute in the following way. We have a set of sources. For example, for the Fink experiment, we have a sequence of pushes. We can assume they are delta function sources or distributed in some way, but the idea is if there were no inclusions, if everything was constant, we somehow have a handle on the solution to that problem. Okay, what do I mean by that? I mean, we know that if we just have the wave that propagates away from that source, we know what that is. That's U0. But now we have inclusions. So now we have a scattered wave. We represent those inclusions by these changes in the shear moduli. And for this part of the talk, I'm assuming that the tau alphas don't change. Okay, and this U0 now satisfies this base problem. Then the scattered wave then satisfies this problem. And we know this from scattering theory. This is not really anything new, except we have this integral differential equation to deal with. The right-hand side it depends on the changes in my material parameters and also on this background wave that's propagating. We know the U0 either exactly or we can compute it. We're using a second-order finite difference method for US, but US now is scattering away. We want to use this outgoing condition. We need somehow for this viscoelastic model to get a perfectly matched layer on the boundaries.
Excuse me.
Yeah.
Tau A was the ratio, if I recall well, of eta and mu. So although the mu changed, eta doesn't change because you changed eta appropriately?
The mu can change without changing eta. Oh, yes, because we're changing eta properly. Yes, yes, yes. It's just for the purposes of these slides. I'm just trying to keep things It's not for the purposes of the actual application. Okay, so now I think the only new thing here, again this appeared in JASA in 2010, is how to do the PML layer. So now the classic way, we were very influenced by a paper by Kalina and Sanka, I don't have that on this slide, I should, in which she does the following. So V is now represented by this term, which we would normally see. And notice I'm just doing this when I have a single equation. We have the system version, but again, it's just to try to keep the notation on the slide down. And so V is a vector. U, in this case, is a scalar, but U is divided now into 3 parts. Each part is somehow connected to this vector, the parts in the vector. And what's the goal here? The goal here is to make these U's damp out in the layer so that we have these damping coefficients that do this. And if we didn't have this term, all of this would be known. But now we have this term and we are able to add it in the following way and achieve our goal, which is have the solutions damp out in the layer and not reflect back, which is exactly what we don't want. Okay, and now to just, there are some, maybe some of the people are computing on this, so there are some technical details about what should be on the grid and what should be on a staggered grid. And also I wanted to just put in this little plot to just make absolutely certain people are aware that although I wrote this in 2D, we're computing in 3D. Okay, now, okay, so let's talk about these arrival times. So we had some, initially we had some interest in understanding theoretically how we get the arrival times from, how we define that in terms of the displacement. I think if you just work with the O'Connell equation, then you have there's a straightforward way to define arrival times of viscosity solutions, but that's not what we have. We have the displacement. So what we wanted to understand is how would we define this arrival time based on the displacement. So we started out with this definition. So it's physical. It seems like it would make sense. Okay, I have a source. It starts a wave propagating. For a long time at this point, nothing happens. It's just sitting there. And then the wave comes and we start seeing some displacement. So we said, okay, let's define this arrival time as, in some sense, the minimum time, the inf over all time, where we have a positive displacement. Seemed reasonable. Okay, we hypothesized that with that definition that it was Lipschitz continuous, and then with that definition we got the O'Connell equation, which of course is what we want. Then we found the following example. So this example says the arrival time looks like this, but at this one point it's here. Okay, what's happening here? We can start a wave and it's propagating, but we can get cancellation on a lower dimensional set for a very long time. Okay, so our theorem is still true, but we need a new definition. Okay, so now we need a new definition, also physical. Okay, so what we used is the following. We said, okay, let's look at the point. We'll say the wave has not arrived there if we have an open neighborhood about that point where nothing is happening. But the minute we can't find such an open neighborhood, then the wave is there. Okay, that's the new definition. And now with this new definition, we can show everything that we want. We can show that it's Lipschitz continuous. We can show that it satisfies the O'Connell equation. Well, that, once we have Lipschitz continuity, we get that from our former proof. And then we show it's the viscosity solution. Now, that's a very special solution that people use. So they're using that when they're solving the O'Connell equation. And it has special properties. I'll put them on the next slide. And we wanted this because we want to use those level set methods, at least an adaptation of those. Okay, to prove the Lipschitz continuity, we use unique continuation. In fact, surprisingly to me, once I started, was that we've used unique continuation several times in different proofs. Okay, showing once we have that, we have the O'Connell equation, that's the old proof. And now to show it's a viscosity solution, again, we use unique continuation. And the definition we're using of this is the following. If this solution is bounded and uniformly continuous, if we have something that lies below it, but it touches this arrival time, and it lies below it in some open V, then in fact the gradient is bigger than 1 over the, at that point, is bigger than 1 over the speed. And if it lies above, but it touches the arrival time surface at this point, then in fact we have the reverse inequality. Okay. Up. I'm going to skip that. They're videotaping. I guess I left it up too long. That's an unpublished result. Okay, so now what actually happens when we have the system? What I was showing you there was a result when we have a single equation. Now, what happens when we have a system is that the first thing that propagates is the compression wave. And then coming behind is the wave we want, which is the shear wave. Okay, so if we have inhomogeneities, we don't have a nice sharp front. We have this scattering of this compression wave. So we can no longer use the previous result, nor can we make some definition like this, because we will never have this sharp front. Okay, so the way that it's done then is to use geometric optics. What we know now is that at the front, we need the highest possible frequency content. We can't produce the front otherwise. So we use this geometric optics expansion, allowing omega to get as large as we like. This is also something that we do standardly when we are looking at the equations of elasticity. Only now when we do this, we look at the expansion in omega. It begins, and we make this assumption, as we've done it, as you do in geometric optics or microlocal analysis, that you have this separation of scales. Omega is big enough that each power somehow separates from the other powers, and we can set those coefficients equal to 0. What we see now is that we have this system of equations with a coefficient matrix then, and it's set equal to 0. We want A naught to be non-zero. It's boring if it's 0. We don't care about that. We care if it's non-zero. So the determinant has to be 0. This looks very similar to what happens in the elastic case, except now we have all these different additional moduli. That's the only new thing that's happening here. What we get out of that are two, once we set that determinant equal to 0, we get these two iconal equations. One of them is for the pressure wave, which is influenced now by all these small spring constants, but lambda again is quite huge. And now we get this second one, which tells us about the wavefront of the shear wave. Okay, this is of order 1, but this guy is really big. Okay, we let omega get large enough that we can interpret phi at this phase phi as the arrival time. And then we have to hypothesize all these things that we want. Okay, now what we would like to know is something about sensitivity. Okay, what do I mean by that? What I mean is we have a data set. We know what the amplitude of the phase would be if we didn't have any inclusion at all. But what we would like to know is what happens to the data when we have an inclusion, and that change, when is that change larger than the noise? Okay? So that's what this little piece here is about. Okay, so this is work with Jean-Marc Youn and Assad Oberai. Assad is one of the people in our group. He's a mechanical engineer. So what happens when we have a stiff inclusion? Well, if it's pretty big, 16 millimeters would be big for us. If it's pretty big, we see this huge amplitude drop, and also we can think of the arrival time. Here are the arrival times. We see this push forward. Visually, we can see this. Okay? But if we make it much smaller, 4 millimeters, we definitely would like to identify something that small. Then when we look at the arrival time, well, if I zoomed in, of course, you could see this. But on the scale of this, you don't see very much. And if we decrease the frequency, now you see much less amplitude drop over here, and you see even less here. Of course, I probably should have zoomed in. What I'm trying to suggest here is that what's going to play a role about sensitivity is the size of the inclusion, the radius, the excitation frequency, that would be the central frequency in the pulse that's propagating, and also the change in the stiffness. Okay, so in this initial result, I'm simply using the wave equation, but Jean-Marc Youn with his students has worked with both the full equations, linear equations of elasticity, and also equations with damping. And this paper will be submitted by the end of the month. His papers maybe a little bit later, those other papers. Okay, so I'm just emphasizing this again. So if we have a large inclusion, then we get a nice amplitude drop. We see the change in the phase or the change in the arrival time. And of course, when it's smaller, we see much less. Visually here, of course, I would have to zoom in for you to see this, but if I plotted the gradient of the arrival time, that would be another story. So that's the thing I'm going to look at. So here's the model that we're using for this sensitivity. We have this inclusion. It's circular. You can think of it in 2D as a cylinder, but the results I'm showing you right now are in 3D, so it's a disk. It has radius r. We have a line source pulse over here, or you can think of it as a planar source pulse if you want. It propagates in. We know exactly what the form is if we don't have an inclusion, and then we have a scattered wave from here. Okay, here's the model, this very simple model in this first result. Mu1 is what we have in the background. Mu2 is what we have in the interior. Okay, I'm assuming everything is real here for this first result. Okay, so I'm not telling you the method at all, and that's probably not fair, but I thought that made sense given what I want to tell you today. So here's the result. In this case, on this slide, I realized this morning, this arrival time, I'm including an omega squared here. So that's probably not fair, but because I'm looking at the relative change, this is now 1 over the square of the speed. This is the arrival time, which is the gradient of the arrival time, which is 1 over the square root of the speed. And so I'm looking at the relative change. So I look at what I have in the background and what I have in the background minus what I have inside the inclusion. The formula that we get, so to get a nice formula, let me go back, we're going to only look at the very center. This has to do with the fact that we can actually write everything down in closed form. It's quite nasty, but we can write it down in closed form. And so at the center, we can get this nice formula. So we see it depends linearly on r squared. This relative change depends linearly on r squared. It depends linearly on omega squared. But notice that if I let r squared get smaller and smaller and smaller, what's dominating here is the contrast.
By asymptotic, you mean small capital R, yes?
Yes, actually omega r.
Omega R.
Small omega r, that's right. Okay, so we made this plot. I see it's cut off there somehow at the bottom. But the plot is supposed to do this. We assume the noise level is 10%. That's 10% in the gradient, in the arrival time. We actually know how to take the gradient, so we keep the noise level the same. And this is without the omega squared now. Now what we're showing you here, the green line is at 300 hertz, so we can detect now smaller inclusions for a given, for higher frequencies. The blue line is 200 hertz. What we have here, this is the contrast. This is the ratio of mu2 divided by mu1. So mu2 in all of this is bigger, and this is in millimeters. Okay, and what you see now is the smallest thing we can detect given the frequency and the contrast. And of course, once we get down to 0, we still have some sort of detection. It has partly to do with the mathematics, of course, but it's telling us that really, if you have enough contrast, really small inclusions could be found with 10%.
For high frequencies?
For high frequency, no, it doesn't matter about the frequency.
But it's only the green that survives.
No, well, it's all of them actually. You only see the green.
Okay.
You only see the green. I don't know how to make 3 colors like that.
Okay.
I'm sure there's a way.
What happens if you have the other contrast ratio?
What's that?
What happens if you have the other contrast ratio?
Oh, we haven't actually done that. That's quite interesting because now we know about diseases for which we get softening. It seems to have that particular problem seems to have a lot of new features. It's not part of this talk. Okay, so again, I'm just repeating. It depends linearly on the square of the frequency. It depends linearly on the square of the radius of the inclusion, and non-linearly on the contrast ratio. Okay, practical matters. Okay, so what we want to do now, we want to calculate this speed. So we're going to get the sum of all those spring constants when we do that. When we go into the frequency domain, which is not part of this talk, then we have more chance to distinguish. But at this way, with the front, this is all we can see. The first step is find that arrival time. Now I'm really talking about practical things. So here's an example of a time trace. Okay, so this part is some kind of bulk motion. You can see that this bulk motion, it comes really from the operator pushing. So we see something happen, right? But we're quite certain that that's the case here because we see sort of something happening at the same time everywhere. And now we see this shear wave propagating. The source now is coming from this side here, and that also is where the ultrasound transducer is. So at the red point, you can see these are particularly nice time traces, I have to tell you. You see this time trace. At the blue point, the black point, you see another one. At the blue point, you see another one. Now what we want to know is how long it took the wave to travel from the red point to the black point, and from the black point to the blue point. And so you can sort of think what you would do is you would try to shift the black curve backwards until it matched the red curve. And then you would try to shift the blue curve backwards until it matched the black curve. Right, so that's kind of the idea. Of course, we don't want to eyeball it. And here's another set. You can see now these don't look quite so similar. Okay, so here's something at a blue point. Here's something at a red point. And now we want to do the same thing. We want to shift this red one back until it matches the blue one. You can see down here that's a much harder thing to do. Okay, and this is typically done with cross correlation. So you just keep shifting backwards, and then for each shift you get a point in the cross correlation and you look for the maximum. Okay, so this is a standard procedure for doing this to find the arrival time. What we observe here is there are a few things that we're not taking into account, which might help us. One is that this thing is spreading, and we exactly expect that, because the information content at different frequencies is traveling at different speeds. So we expect that as we get deeper in the medium, we get more spreading. The second is we know now, at least theoretically, that the arrival time should be continuous. The third thing we know is that the spreading probably is smooth. Furthermore, we know that as we go further away from the source, the arrival time should increase. As we go further away from the source, the spreading should become more. Okay, so if I don't take into account all those things I told you at the end, and all I do is use cross correlation, we get something that looks like this. Not so pretty. Okay, we do see the push forward here. We see a lot of small inclusions. We see pile-ups here that we don't really expect. Okay, but if I add in all those things I was just telling you about, I get a set of arrival times that looks like this. This looks much nicer. Okay, so each one of these is a constant arrival time curve. So this is practical matters now when we're dealing with data. So how are we doing this? Well, instead of doing this cross-correlation procedure, as I told you before, we try to model a wave packet in some way. And that really depends on the experiment, and I'll show you a couple of models that we're using. And we introduce a spreading parameter. We have the arrival time, and we say that our model parameter is going to spread as omega, we'll fix it so as omega decreases, so omega should decrease as we go deeper in the medium. So we add in all these extra things. Here is a time trace. Here is our model. Now we're going to minimize all these other things, so we put a minus instead of instead of a plus here. And now this one tells us that omega has to change continuously. This one tells us that omega decreases as we go deeper in the medium. This one tells us that the time trace the arrival time has to increase as we go deeper in the medium, and this tells us we want things to be continuous. And then we allow a little fudge factor here, so things, we can allow a few wiggles, let's put it like that. Okay, so this we need something here, but it doesn't seem too sensitive to the value as long as we're reasonable. Okay, so this is what we pick here for comparison is the median of values at nearby points. And now how do we pick lambda? Well, lambda has to be scaled according to the time trace, the amplitude of the time trace. We don't really bother with trying to scale the model wave packet. And then we put in this number 0.15, which is working for us unbelievably well, but we don't have a proof for why that works. Okay, again, practical. Okay, so if we have an oscillatory signal, we pick a sine function or a cosine function. This interior radiation force push tends to give us a time trace that looks like the blue one or like the red one, and we're using a sinc function in that particular case. And we have a very bright undergraduate that I didn't mention, Michael Puthawami, and he is looking at automatically picking what the reference signal should be. Okay, now we have this arrival time, we have the Eikonel equation, so why don't we just compute the gradient and then we're done? Okay. It has a lot of noise in it, the arrival time has some noise in it. We have, using a technique that was in Math of Computation by Anderson and Hagelin, we can take a lot of different difference quotients and do some kind of averaging, and by picking all these, the number that we choose and also the size of the difference quotient and the grid size in a way that's, that helps us, what I mean by help is that this 2 divided by all this stuff in the denominator gives us 1. Then we can keep the variance in the noise the same when we take the derivative. So that's a good thing. And we do this, we sometimes do this. But what the difficulty with this is the following. If we take the arrival time and it has Gaussian noise, notice the gradient will still have Gaussian noise. But we're taking 1 over this. And when we look at 1 over a random variable, where the random variable is normally distributed, we get something which is more Cauchy-like. Okay, what do I mean by a Cauchy distribution? What I mean by that is that it has a very heavy tail. In fact, in general, it has infinite variance. Okay, so this is not something that we really welcome. We would really rather do something else. Okay, so what we are doing is the following. We do that other method sometimes, I have to be honest, but this method works better for us. So it's based on the simplest idea you can think of. It's based on the fact that speed is distance divided by time. Okay, so let's look at curves of constant arrival time. And now the good thing about looking at curves of constant arrival time as compared to the method I just told you is that when we compute the gradient, if in fact the arrival time is not changing very much, then the noise is a much bigger percentage of the difference. Okay, so this is a problem. Okay, however, if we look at lines of constant arrival time, then they become much further spaced apart when the speed goes up. So this is a good thing. So it suggests that the variance in the noise doesn't increase when we have increased speed. So what we're doing is we take the point x, we look at all the points on, say, the arrival time curve t hat of x plus delta t, and we take the minimum distance to the grid points that are on this curve. Okay? And then, or we can get a first order method that way. Or we can look at a second order method by going to the front and going to the back. This very simple method has better noise characteristics. If you know about, and I'll tell you, we have a much more sophisticated way of computing, which is much faster. This is extremely slow. But if you know about order statistics, if you take several random variables, say normally distributed random variables, and then you take the minimum of those, and you look at the mean, what happens is the mean is decreased. And that's exactly what we see with this method. We do see some undershooting. So it has that disadvantage. Okay, but to make the algorithm fast, you can use level set methods. So the idea is this: you have at any constant time, you have your arrival time curve. I'm doing this now in 2 dimensions, could be done in 3. Then you sort of thicken that up. You find a function phi which is 0 there, and at every point nearby, we don't need it very thick, at every point nearby, we say that the value of phi is the distance from that point to the curve. And then the phi satisfies this Econol equation. And okay, and that's how we construct phi, and there's a fast way to do this. And then we already know that t hat is Lipschitz continuous if we have the true thing. That means phi is Lipschitz continuous. We can apply the chain rule. Okay, we can move this term over on the right-hand side, take the length of everything, of these vectors. We know the gradient of phi is 1, and we get this very simple equation. So what this does is it takes this 1 over the gradient into something which is linear. It has that nice feature. Okay, now, once we have that, then again, we can take a first order method or a second order method, and this is completely equivalent. This is in a 2006 paper to this distance, what we call the distance method. These level set methods are order m or order m log n, depending upon which one you implement, and m is the number of spatial grid points. Okay, so how does all this do? That'll be the last part of the talk. I think I'm doing about right. Okay, so this is the inclusion. This is a data set we got from Fink. It was particularly problematic for them. And this is what happened when we determine the arrival time with correlation. We get lots of artifacts. This is what happens when we have, when we add in all those additional constraints in order to get the arrival time. Notice also we have this kind of wing effect here. This seems to have something to do with the fact that we're imaging in it's a kind of diffraction effect, that we're imaging in 2D when we have 3D data, when the wave is propagating in 3D. Okay, this is the ultrasound image I showed you in the very beginning, and here we get the stiffness image here of this inclusion, this 1 centimeter inclusion, quite aggressive cancer that this woman had. Okay, so we were pretty excited when we saw that. But now we're thinking differently, as I mentioned. This is a very small cancer that was identified here by the radiologist and biopsied and recognized as a very aggressive cancer. And this is the stiffness image here that we get. This is a cyst. I'm not really talking about this, but it's on this slide. I'll just mention briefly. You can have a cyst. It has a nice, well-defined boundary. That's not what we see here in the top, but still is filled in. So it's not clear what's inside. What they would like to know is this fluid inside, in which case everything is fine. And so we have a fluid identification algorithm, and this is the result of that. So, but that's not, I'm not actually explaining that in this. Just say that we have that. Okay, here's the prostate. Okay, so here is the ultrasound image. The radiologist does think there's something here. I couldn't see it. The way the experiment is done, we first look in the ultrasound image. Then they mark where they are. Then we do this, we do the biomechanical image. And then with that marking, the pathologist makes a slice in this, presumably in the same image plane as much as possible. And this is what they identified as the cancerous area. I'll show you another one of those. Okay, here's the ultrasound image over here. So this is, this histology slide is rotated somewhat, as you can see. And there are 2 cancers identified here by the radiologist, by the pathologist, and this is our image. Now, in this particular set of data, there were 15 patients. We had 3 slices to look at, and so that's 45. That's not huge. It's nothing like 1,000 or anything. And for people who know about these things, sensitivity and specificity and accuracy, we were about the 85% in terms of identifying things. Okay, so that's it for this talk. I have another talk about frequency-dependent things, but that's not here. We're looking at viscoelastic models. We want those when we're looking at arrival time to have finite propagation speed. Our particular choice here is this linear solid model, which is an integral differential model. Okay, we have theoretical equivalence between the displacement, identified arrival time, and the viscosity solution of the Econol equation. We've created some sensitivity formulas. We have optimization methods for the arrival time identification, and then I showed you some of our images that we get for cancer identification. Okay, thank you very much.
questions.
Yeah,
One is, you compare with ultrasound, where of course it is clear that you do great.
yeah.
But what about other modalities? And that's one question. The second question is mathematically, from all this beautiful analysis you present us at the beginning of the talk,
Yeah,
for the final cancer identification,
yes.
which actually part of the mathematics was used? I understand that it was used, the iconal equation in its various disguises
Right,
of how to get the arrival time,
right.
and what else?
Well, we use the interpretation of what the speed is used. Okay, so that comes from the viscoelastic model. We use the smoothness. We have to use the smoothness for the level set method that we prove for the arrival time. What else do we actually use? I think when you're looking at the way all this works, the way I see it anyway, is the following. You develop all this nice mathematics, okay? It tells you what you should see if you know known properties. When you know known properties, that's when you have a phantom in the laboratory. So you try to do the best match there. You match with a phantom for your model, what you predict with the model, and what the phantom tells you. But after that, you have tissue. You don't really know what's there, right? So that's really that's the only way one can proceed. Exactly.
And going back to my first question, for example, suppose you do a CT, will you still do better?
Suppose we do what?
A CAT scan for something.
Oh, I don't know yet. We don't know yet. We don't have that kind of data. There is one person who has, his name is Barr. I believe he's in Kentucky. I'm not 100% certain. No, he's in Ohio. And he has done he has done a 1,000 person study. And he does extremely well. He's in the 90-some percentiles with all those things that I was just telling you. Sensitivity, specificity, and accuracy. I think you know what accuracy is. Sensitivity and specificity, the main thing I could say about that is one of them tells you something about how much you overestimate the negatives, and one of them tells you something about how much you overestimate the positives. Of course, it could look really great if I said everybody had cancer, then I would say, okay, I identify it 100% of the time, right? Well, of course, I tell a lot of people who don't have cancer, they have cancer. Yeah.
No, that's very nice. One last thing, if I may.
Yeah.
In the first transparency, in the first image, you said that the pathological tissue will have 100% increase, but should not be the case always. I mean, it depends on what kind of pathological issue you have.
Yes, that's right. But the point of that is to say that for most cancers, when they take the right, okay, good. So I shouldn't have skipped the one slide. It's okay, I have it. Sorry, this is going slower than I know. Here it is. Okay. So what these people did is the following.
Very good, yes.
Yeah, so we have this data. So and the first set of data is done by Kathy Nightingale in her laboratory. She's at Duke. And so she was looking at breast fatty tissue, and then that's where the fibroadenomas usually grow. And so she was looking around the fibroadenoma, and she got a wave speed that looks like this. And in the fibroadenoma, she got a wave speed that looks like this. So this is...
Okay, consistent.
Okay. And then Dick Eman and his laboratory for magnetic resonance imaging based, which I didn't talk about at all, but so now we can see what he's looking at: breast fatty tissue, normal, breast glandular tissue, which is where most cancer resides, and breast cancer tissue. And now we see what the difference is. So now in fatty tissue, he gets something smaller than this, right?
But still larger than...
But this is larger. This is just glandular tissue, and this now is much, much larger. This is actually a very important point, because for some things that are being measured, what you're really measuring, turns out, is that the cancer is in glandular tissue. Turns out there's not that much difference between, but not for biomechanics, but for some other things that are being used to image.
Okay.
Okay?
Okay.
So
Yeah.
this question kind of comes back to the beginning that they're both mechanical wave propagations. So ultrasound and this technique are both mechanical wave propagations through the tissue. What exactly is the difference? So in ultrasound, you just get a reflection usually, don't you?
Well, ultrasound, you get a reflection, that's absolutely right, but it's based entirely on the pressure wave or the compression wave.
Right.
Okay, so what we are trying to do is image the shear wave properties.
So which is behind it and
Right.
more sensitive, although weaker.
And so, the reason this works, I'll make this point again, is that when we take the ultrasound data, when the RFIQ signal is acquired, we can assume the shear wave is essentially stationary, because we have this huge order of magnitude difference.
Okay, and also with ultrasound, it's a reflection that you get. So
Yes.
there's a transducer that transmits and receives.
Yes.
Do you need to measure through the tissue, or
We're not using that at all, and in fact, I don't think measuring the transmitted wave would be helpful well, it would be helpful in one way. Okay, so if we had transmitted data, we would have a much easier time of finding out the compression wave speed. When you're looking at the ultrasound data, what has been already proved is that what you are really getting is reflection from edges or from discontinuities or from big, quick changes. And that's really all that you're getting. And, but if you get transmission, then you can actually recover what those variable wave speeds are within those inclusions. But I don't think that would help us make the movie, except that if we knew what those changes were, then we would be better able to identify on the time trace what represents the scattering volume. Right? So it would help that.
any more questions? In that case, we'll
Thank
take the
you very
speaker
much.
again.